Imagine a cosmic wanderer, a silent voyager from the vast, uncharted depths between stars, making an unannounced appearance in our celestial neighborhood. Not a star, not a planet, but something far more enigmatic. In the autumn of 2017, the Pan-STARRS 1 telescope in Hawaii, a vigilant sentinel scanning the night sky, detected just such an object. It was a fleeting glimpse, a faint streak of light moving with impossible speed, a celestial bullet tearing through the cosmic void. This was 1I/2017 U1, soon to be christened Oumuamua, Hawaiian for scout or messenger. But Oumuamua was no ordinary messenger. Its arrival wasn't merely a scientific curiosity. It was a profound challenge to our understanding of the universe. This was the first confirmed interstellar object ever observed passing through our solar system. A true alien in the most literal sense. Its trajectory, a hyperbolic arc, unequivocally declared its origins beyond the gravitational embrace of our Sun. It was an uninvited guest, a silent intruder from another star system, and its very presence ignited a firestorm of scientific debate and public fascination. From the moment of its discovery, Oumuamua defied every expectation. It was unlike any asteroid or comet we had ever encountered. Its shape, initially inferred from its fluctuating brightness, was bizarrely elongated, like a cosmic cigar or a flat pancake, tumbling end over end through space. But the true enigma lay not in its form, but in its behavior. As it sped away from the Sun, Oumuamua inexplicably accelerated, veering off its predicted gravitational path. This non-gravitational acceleration, a subtle yet undeniable push, was the kind of behavior typically associated with comets, which release gas and dust as they warm up. Yet, Oumuamua displayed no such cometary tail, no visible shroud of escaping material. It was a ghost in the cosmic machine, accelerating without a trace. This paradox sent shockwaves through the astronomical community. How could an object accelerate without outgassing? Was it made of some exotic material? Or, as some daringly speculated, was it something far more extraordinary? A technological artifact? A derelict probe? A light sail from an alien civilization? The questions surrounding Oumuamua became a crucible for scientific inquiry, pushing the boundaries of our imagination and forcing us to confront the possibility of phenomena beyond our current understanding. For years, Oumuamua remained an isolated anomaly, a singular mystery that continued to baffle and intrigue. It was a cosmic riddle with no easy answer, a testament to the universe's capacity for surprise. But then, in July 2025, the universe delivered another surprise. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, a network of vigilant telescopes designed to protect our planet from cosmic impacts, detected a new interstellar visitor. This object, designated 3I/ATLAS, was also from beyond our solar system. And while its arrival might seem like a mere echo of Oumuamua's, 3I Atlas was different, profoundly different. Its behavior, its very nature, would not only provide crucial context for Oumuamua's strangeness, but would in fact change everything we thought we knew about these interstellar wanderers. This is the story of two interstellar objects, one that defied explanation and another that, by its very normalcy, made the first even more extraordinary. This is the story of how Oumuamua was strange, but 3I Atlas changes everything. The discovery of Oumuamua was a triumph of modern astronomical surveying. On October 19, 2017, the Panoramic Survey Telescope, and Rapid Response System, or PAN-STARS 1 in Hawaii, a state-of-the-art facility designed to detect near-Earth objects, captured faint images of a rapidly moving point of light. Initially, it was catalogued as an asteroid. However, further observations quickly revealed its true, groundbreaking nature. Its trajectory was not the elliptical path characteristic of objects gravitationally bound to our Sun. Instead, it followed a hyperbolic trajectory, meaning it had too much velocity to be captured by the Sun's gravity. This was the unmistakable signature of an object originating from interstellar space. Its velocity, a staggering 87.3 kilometers per second, approximately 196,000 miles per hour, relative to the Sun, was far greater than any object known to be orbiting our star. This extreme speed, combined with its hyperbolic path, left no doubt. Oumuamua was an interstellar interloper, a cosmic nomad on a one-way journey through our solar system. Its inbound trajectory suggested it came from the general direction of the star Vega in the constellation Lyra, though its true origin star system remains unknown, having likely been ejected from its home long ago during a gravitational slingshot encounter with a giant planet. One of the first perplexing characteristics of Oumuamua was its highly unusual shape. As it tumbled through space, its brightness varied dramatically, suggesting an extreme elongation. Initial models proposed a cigar-like shape with a length-to-width ratio of at least 5:1, possibly even 10:1. To put this into perspective, imagine a cosmic needle, hundreds of meters long but only tens of meters wide. Later studies also considered a pancake-like or flattened shape as a possibility, equally unusual for a natural celestial body. This extreme aspect ratio was unlike anything seen in our solar system's asteroids or comets, which tend to be more spherical or irregularly shaped, but rarely so elongated. Furthermore, Oumuamua exhibited an erratic, tumbling spin. Instead of rotating neatly around a single axis, it appeared to be rotating around multiple axes simultaneously, like a football thrown with a wobbly spiral. This complex rotational state, combined with its unusual shape, made it even more challenging to understand its physical properties and origin. The tumbling motion could have been a result of past collisions or outgassing events, but without a visible coma, the latter remained a mystery. Perhaps the most baffling aspect of Oumuamua was the complete absence of a cometary tail or coma. Comets, often described as dirty snowballs, release gas and dust as they approach the Sun and are heated, forming a visible coma and often a spectacular tail. This process, known as outgassing, is a defining characteristic of comets and is also responsible for the subtle, non-gravitational forces that can alter their orbits. Yet, Oumuamua, despite its close approach to the Sun, showed no such activity. Telescopes, including the Hubble Space Telescope, meticulously searched for any signs of a dust cloud or a tail, but found none. This absence was a critical piece of the puzzle. If Oumuamua was a comet, why wasn't it behaving like one? Its lack of a visible coma suggested that it either contained very little volatile material or that any outgassing was occurring in a way that didn't produce detectable dust. This observation immediately cast doubt on the idea that it was a typical interstellar comet and fueled speculation about its true nature. The most perplexing and scientifically significant aspect of Oumuamua's behavior was its anomalous acceleration after its closest approach to the Sun perihelion, on September 9th, 2017, Oumuamua began to speed up, deviating from the path predicted by gravity alone. This wasn't a massive, sudden burst of speed, but a subtle, continuous push, equivalent to a tiny force of about 5 micrometers per second squared. While seemingly insignificant, this deviation was precisely measured and confirmed by multiple independent observations. It was a clear indication that something other than the Sun's gravity was influencing its motion. For solar system comets, such non-gravitational acceleration is a common phenomenon, caused by the rocket-like thrust generated as volatile ices on their surface sublimate and escape into space. This outgassing creates a jet effect, subtly altering the comet's trajectory. However, as established, Oumuamua showed no visible signs of outgassing. This created a profound dilemma. How could it be accelerating like a comet without the telltale signs of cometary activity? This contradiction was at the heart of the Oumuamua mystery, leading scientists down a rabbit hole of unconventional theories and hypotheses. The implications were immense. Either our understanding of cometary physics was incomplete, or Oumuamua was something entirely new, something that defied our established categories of celestial objects. The initial and most straightforward explanation for Oumuamua's non-gravitational acceleration was outgassing, similar to how comets behave. However, the lack of a visible coma or tail presented a significant challenge to this theory. If outgassing was indeed occurring, it had to be of a very specific and unusual kind. Scientists proposed several scenarios to reconcile the acceleration with the absence of visible dust. Perhaps Oumuamua was outgassing primarily hydrogen or helium, which are transparent and would not produce a visible dust cloud. However, these highly volatile elements would likely have sublimated away during its long journey through interstellar space, making it improbable that enough remained to cause the observed acceleration. Another idea was that the outgassing was highly directional, perhaps from a small, localized vent that was not easily observable from Earth. This could explain the acceleration without a widespread coma, but it still didn't fully address the lack of any detectable dust. The possibility of exotic ice compositions was also considered. For instance, if Oumuamua contained significant amounts of supervolatiles like molecular hydrogen ice, its sublimation could provide the necessary thrust without producing a visible dust tail. However, such materials are extremely volatile and would require Oumuamua to have formed in an exceptionally cold environment and remained pristine throughout its interstellar journey, which is a very specific set of conditions. Despite these attempts, the outgassing explanation remained problematic. The absence of a visible coma was a persistent thorn in the side of conventional cometary models, forcing astronomers to consider more radical alternatives. The struggle to explain Oumuamua's behavior within the framework of traditional cometary physics led to the development of more exotic hypotheses, primarily focusing on its potential composition. Two prominent theories emerged, suggesting that Oumuamua might be made of unusual types of ice. One compelling theory, put forth by researchers like Darryl Seligman and Gregory Laughlin, proposed that Oumuamua was a cosmic iceberg composed primarily of molecular hydrogen ice. In this scenario, the non-gravitational acceleration would be caused by the sublimation of this highly volatile ice. As hydrogen ice sublimates, it produces gas but no dust, thus explaining the lack of a visible coma. The challenge with this theory is the extreme fragility of hydrogen ice. It would require Oumuamua to have formed in an incredibly cold environment, such as the core of a giant molecular cloud, and to have remained at extremely low temperatures throughout its journey to avoid complete sublimation. While theoretically possible, the conditions for its formation and survival are very specific and rare. Another intriguing hypothesis proposed by researchers from Arizona State University suggested that Oumuamua was a fragment of a Pluto-like exoplanet composed primarily of solid nitrogen ice. This theory posits that Oumuamua was chipped off a larger icy body in another star system, similar to how objects are ejected from our own Kuiper belt. Nitrogen ice, like hydrogen ice, would sublimate without producing a visible dust tail, thus explaining the missing coma. Furthermore, the reflectivity of nitrogen ice could account for Oumuamua's observed brightness variations. This theory also offered an explanation for its elongated shape, suggesting it was a shard from a larger impact event. The nitrogen ice hypothesis gained some traction as it provided a more robust explanation for the observed phenomena compared to the hydrogen ice theory. As nitrogen ice is less volatile and could survive the interstellar journey more readily. These exotic ice hypotheses represented a significant departure from traditional cometry models, forcing astronomers to consider the possibility of entirely new classes of interstellar objects with compositions unlike anything we typically encounter in our own solar system. They highlighted the vast diversity of planetary systems that could exist beyond our own and the unexpected materials they might produce. Amidst the scientific struggle to explain Oumuamua's bizarre characteristics, a highly controversial yet undeniably captivating hypothesis emerged from Harvard University. Professor Avi Loeb, a renowned theoretical physicist and former chair of Harvard's astronomy department, proposed that Oumuamua might not be a natural object at all, but rather an artificial one, a piece of alien technology. Loeb's argument was built upon the cumulative strangeness of Oumuamua. He pointed to its extreme elongation, which he suggested was more consistent with a manufactured object like a light sail, a theoretical spacecraft propelled by radiation pressure from a star. He also emphasized the unexplained non-gravitational acceleration, arguing that if it wasn't due to outgassing, then radiation pressure acting on a very thin, wide object could provide the necessary thrust. In his view, a natural object would have to be incredibly thin and wide to experience such significant radiation pressure, a shape that is highly improbable for a naturally formed celestial body. Loeb and his collaborator Shmuel Bialy published a paper in 2018 titled "Could Oumuamua Be a Light Sail from Another Civilization?", which immediately ignited a firestorm of debate within the scientific community. While many astronomers acknowledged the perplexing nature of Oumuamua, the vast majority were highly skeptical of the alien hypothesis. The scientific method demands extraordinary evidence for extraordinary claims, and for most, the evidence for Oumuamua being alien technology was circumstantial at best. Critics argued that while Oumuamua was unusual, there were still plausible natural explanations, even if they stretched the boundaries of our current understanding. they emphasized the importance of exhausting all natural explanations before resorting to extraterrestrial ones. Despite the widespread skepticism, Loeb continued to champion his hypothesis, arguing that the scientific community was too quick to dismiss the possibility of alien technology due to a form of intellectual conservatism. He maintained that the anomalous acceleration, combined with the unusual shape, warranted serious consideration of an artificial origin. His work, while controversial, undeniably brought Oumuamua into the public consciousness in an unprecedented way, sparking discussions about the possibility of intelligent life beyond Earth and the implications of encountering such a visitor. The alien hypothesis, regardless of its scientific acceptance, served to highlight just how truly baffling Oumuamua was. It forced scientists to re-examine their assumptions and consider possibilities that were once confined to the realm of science fiction. The debate surrounding Oumuamua's origin underscored the profound questions it raised about the universe and our place within it. The perplexing arrival of Oumuamua, coupled with the ongoing threat of asteroid impacts, underscored a critical need for enhanced planetary defense capabilities. While astronomers had long been tracking near-Earth objects, the discovery of an interstellar object moving at such high velocities highlighted a new class of potential cosmic threats and scientific opportunities. It became clear that a more comprehensive and rapid sky scanning system was required, one that could detect not only objects within our solar system, but also those venturing in from the vast interstellar medium. This urgent need led to the development of the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Conceived and operated by the University of Hawaii and generously funded by NASA, ATLAS was designed to be a robotic astronomical survey and early warning system. Its primary mission: to provide a last alert for objects that might be on a collision course with Earth, giving humanity crucial days or even weeks of warning. But beyond planetary defense, ATLAS also held the promise of discovering more interstellar visitors, unraveling the mysteries they carried from distant star systems. ATLAS is not a single, monolithic telescope, but rather a distributed network of 4 robotic telescopes strategically located across the globe. 2 telescopes are situated in Hawaii, Haleakala and Mauna Loa, one in Chile, Cerro Tololo, and another in South Africa, Sutherland. This global distribution is crucial as it allows ATLAS to continuously monitor the entire observable night sky, regardless of local weather conditions or time of day. If one site is clouded over, another can pick up the slack, ensuring uninterrupted coverage. Each ATLAS telescope is relatively small, with a 0.5 meter aperture, but they are equipped with highly sensitive cameras capable of capturing wide fields of view. The system works by taking multiple images of the same patch of sky over short periods. Sophisticated software then analyzes these images, looking for any moving objects. Because asteroids and comets appear as streaks or moving points against the stationary background of stars, the software can quickly identify potential threats. The data from all 4 telescopes is then fed into a central processing unit, which calculates the object's trajectory and assesses any potential impact risk to Earth. One of ATLAS's key strengths is its rapid scanning capability. The entire dark sky visible from its locations can be scanned up to 4 times every night. This allows for quick detection of fast-moving objects, providing valuable lead time. For instance, Atlas is designed to provide a 1-week warning for a 50-meter city-killer asteroid and up to 3 weeks for a 150-meter object. Enough time for emergency preparedness and potentially even mitigation efforts. The significance of systems like Atlas cannot be overstated. Early detection of potentially hazardous objects is the cornerstone of planetary defense. Without adequate warning, an unexpected impact could have catastrophic consequences, ranging from regional devastation to global climate disruption, depending on the size of the object. Atlas provides several critical advantages. Time for response. Even a few days' warning can make a monumental difference. It allows for precise trajectory calculations, enabling authorities to determine the impact location and potential damage. This information is vital for issuing warnings, initiating evacuations, and deploying emergency response teams. Mitigation opportunities. While deflecting a large asteroid is a complex undertaking, early detection opens up possibilities for mitigation strategies. These could range from soft options like civil defense and evacuation plans to hard options like kinetic impactors or gravity tractors, though these require significant lead time and technological readiness. Scientific study. Beyond defense, early detection also provides invaluable opportunities for scientific study. When a new object, especially an interstellar one, is discovered, astronomers can quickly mobilize resources, from ground-based telescopes to space-based observatories like Hubble and James Webb, to gather as much data as possible. This allows for detailed characterization of the object's composition, origin, and behavior, providing unprecedented insights into the formation and evolution of planetary systems beyond our own. In essence, ATLAS acts as humanity's cosmic radar, constantly sweeping the skies for unexpected visitors. Its development and operational success represent a significant leap forward in our ability to protect our planet and expand our understanding of the dynamic universe we inhabit. And it was this very system that would soon deliver another interstellar surprise, one that would shed new light on the enduring mystery of Oumuamua. Just as the scientific community was settling into the prolonged enigma of Oumuamua, the universe, in its infinite capacity for surprise, delivered another interstellar guest. In July 2025, the vigilant eyes of the Atlas system, our planetary defense network, detected a new object streaking through the cosmos. Initially designated C/2025A1, its trajectory quickly revealed a familiar, yet still astonishing characteristic: a hyperbolic orbit, confirming its origin from beyond our solar system. This was the third confirmed interstellar object to visit our cosmic neighborhood, and it was soon formally named 3I Atlas. The discovery of 3I Atlas was a testament to the foresight and effectiveness of the ATLAS system. Unlike Oumuamua, which was discovered on its outbound journey, 3I Atlas was identified much earlier, allowing astronomers to track its inbound path and prepare for extensive observations. This early detection provided an unprecedented opportunity to study an interstellar object from its approach, offering a richer dataset than was available for its enigmatic predecessor. What immediately set 3I Atlas apart from Oumuamua was its undeniable cometary nature. As it drew closer to the Sun, 3I Atlas began to exhibit all the classic signs of a comet. It developed a distinct coma, a fuzzy, diffuse envelope of gas and dust surrounding its nucleus, and a growing tail stretching millions of kilometers into space. Telescopic observations, including those from the Hubble Space Telescope, clearly showed the sublimation of volatile ices from its surface, creating the characteristic cometary activity. This behavior was a stark contrast to Oumuamua, which remained stubbornly inert despite its close solar approach. 3I Atlas, on the other hand, behaved exactly as a comet from our own solar system would, albeit one on an interstellar trajectory. Its activity confirmed that the fundamental processes of cometary outgassing are universal, occurring in other star systems just as they do in ours. This normalcy, paradoxically, made 3I Atlas incredibly significant. While still undergoing detailed study, initial observations of 3I Atlas have provided valuable insights into its characteristics. It is estimated to be significantly larger than Oumuamua, potentially tens to hundreds of times more massive. Its composition appears to be typical of a comet, rich in water ice and other volatile compounds that sublimate when heated by the sun. Its trajectory, while hyperbolic, was less extreme than Oumuamua's, suggesting a slightly different interstellar origin or ejection mechanism. 3. I-Atlas's journey through our solar system has been meticulously tracked, allowing for precise calculations of its path and future trajectory. It is a true interstellar wanderer, having likely been ejected from its home star system eons ago, traversing the vast emptiness between stars before its chance encounter with our Sun. Its presence provides a tangible link to other planetary systems, offering a rare opportunity to study pristine material from beyond our cosmic doorstep. The arrival of 3I Atlas provided astronomers with an invaluable comparative dataset, allowing for a direct side-by-side analysis of two interstellar objects. While both share the extraordinary distinction of having originated from outside our solar system, their differences are as profound as their similarities. This comparison is not merely academic, it is the key to unlocking the deeper mysteries of Oumuamua and understanding the true diversity of interstellar visitors. Both are interstellar, yet their behavior within our solar system diverged dramatically. Oumuamua was the silent, accelerating enigma. 3I Atlas is the active, outgassing comet. This fundamental difference is where the true revelation lies. The existence of 3I Atlas, a perfectly normal interstellar comet, fundamentally changes our perspective on Oumuamua. Before 3I Atlas, it was possible to argue that perhaps all interstellar objects behaved strangely, or that our understanding of interstellar comets was simply incomplete. But now, with a clear example of an interstellar object behaving exactly as expected, Oumuamua's anomalies become even more pronounced, and frankly, more bizarre. 3. I-Atlas serves as a crucial control group. It demonstrates that interstellar comets can and do exhibit outgassing and form tails, just like their solar system counterparts. This makes Oumuamua's lack of activity even more puzzling. If it was a comet, why didn't it outgas visibly? If it was an asteroid, what caused its acceleration? The presence of 3I Atlas forces us to re-evaluate all the proposed natural explanations for Oumuamua. If hydrogen ice or nitrogen ice were viable explanations for Oumuamua, why didn't 3I Atlas, also an interstellar object, exhibit similar non-cometary behavior? the fact that 3I Atlas behaved exactly as a comet should makes Oumuamua's unique properties stand out even more sharply. This comparison lends more weight to the idea that Oumuamua was truly an outlier, an object that defies easy categorization within our current understanding of natural celestial bodies. It doesn't necessarily prove the alien hypothesis, but it certainly makes the natural explanations for Oumuamua seem less universally applicable to interstellar objects. The universe, it seems, is far more diverse and surprising than we had imagined, and Oumuamua remains a profound anomaly, even in the light of new discoveries. The comparative study of Oumuamua and 3I Atlas has profound scientific implications, reshaping our understanding of interstellar objects and the processes that govern them. Firstly, 3I Atlas confirms that interstellar comets formed in other star systems can indeed behave in a manner consistent with our current cometary models. This provides a crucial baseline, validating our understanding of how volatile-rich bodies interact with stellar radiation, regardless of their origin. It suggests that the fundamental physics governing cometary activity are universal, operating similarly across the vast expanse of the galaxy. This is a significant finding, as it allows astronomers to apply established cometary science to objects originating from entirely different stellar environments. Secondly, and perhaps more importantly, the stark contrast between the two objects highlights the extreme uniqueness of Oumuamua. It forces astronomers to consider that Oumuamua might represent an entirely new class of celestial object, one that doesn't fit neatly into the categories of asteroid or comet. This could mean unusual formation environments. Oumuamua might have formed in an environment so radically different from our own solar system that it produced materials or structures we have yet to encounter. For example, if it truly was a nitrogen iceberg, it would imply the existence of exoplanetary systems with conditions conducive to forming such large, solid nitrogen bodies. This would necessitate a re-evaluation of our models for planet formation, suggesting that the diversity of planetary compositions is far greater than previously imagined. Such environments might include regions of protoplanetary disks with extremely low temperatures or unique chemical abundances, leading to the condensation of highly volatile compounds that are rare in our own solar system. The non-gravitational acceleration without visible outgassing strongly suggests an exotic composition. While the hydrogen and nitrogen ice theories attempt to address this, the comparison with 3I Atlas makes them seem less compelling as universal explanations for interstellar objects. This pushes the boundaries of material science in astrophysics, prompting searches for other potential volatile materials that could behave in such a manner. Researchers are now exploring the possibility of other supervolatiles, or even complex organic molecules that could sublimate without producing a detectable dust tail. The challenge lies in identifying materials that are stable enough to survive interstellar travel, but volatile enough to explain the observed acceleration. While still highly controversial, the alien hypothesis gains a subtle, indirect boost from the 3I Atlas comparison. If a natural interstellar object, 3I Atlas, behaves exactly as expected, then the object that doesn't behave as expected, Oumuamua, becomes even more anomalous. This doesn't validate the alien hypothesis, but it certainly keeps the conversation alive and underscores the profound mystery that Oumuamua represents. The scientific method demands that all plausible explanations be considered, and for some, the persistent anomalies of Oumuamua, especially in light of 3I Atlas's normalcy, continue to point towards a non-natural origin. This ongoing debate highlights the philosophical implications of encountering objects that defy our current scientific understanding. Finally, the discovery of both Oumuamua and 3I Atlas has opened a new frontier in astronomy, the study of interstellar objects. These cosmic wanderers offer a unique opportunity to sample material from other star systems, providing direct insights into the composition of exoplanets, the processes of planet formation beyond our solar system, and the dynamics of stellar systems. They are literal messengers from other worlds, carrying secrets encoded in their very being. The comparison between these two objects is not just about solving a puzzle, it's about expanding our cosmic horizons and understanding the true diversity of the universe. It's about recognizing that our solar system is just one small corner of a vast and varied cosmos, and that the objects passing through it can tell us much about the worlds beyond. The arrival of Oumuamua and 3I Atlas has irrevocably altered the landscape of astronomy, transforming the theoretical concept of interstellar objects into a tangible reality. This new frontier in space exploration is now a vibrant field of research, with scientists around the globe actively pursuing strategies to detect, track, and ultimately understand these cosmic interlopers. The future of interstellar object research is multifaceted, encompassing enhanced detection capabilities, dedicated missions, and a deeper theoretical understanding of their origins and implications. The primary focus for the immediate future is to increase our rate of discovery of interstellar objects. While Atlas has proven its worth, other ground-based and space-based observatories are being refined and developed with interstellar object detection in mind. Projects like the Vera C. Rubin Observatory, formerly the Large Synoptic Survey Telescope, LSST, currently under construction in Chile, are poised to revolutionize our ability to find these elusive visitors. The Rubin Observatory, with its massive 8.4-meter primary mirror and a camera capable of imaging the entire visible sky every few nights, will generate an unprecedented volume of astronomical data. Its sheer survey power is expected to detect several interstellar objects per year, dramatically increasing our sample size and providing a statistical basis for understanding their population, distribution, and characteristics. This will allow astronomers to move beyond studying individual anomalies and begin to characterize the overall population of interstellar objects, identifying commonalities and variations that can shed light on their origins. Beyond dedicated survey telescopes, existing observatories are also adapting their search strategies. The Pan-STARRS system, which discovered Oumuamua, continues its work, and other wide-field telescopes are being optimized for rapid detection of fast-moving objects. The integration of artificial intelligence and machine learning algorithms into data analysis pipelines is also crucial. These advanced algorithms can sift through vast datasets, identify subtle anomalies, and flag potential interstellar objects much faster and more efficiently than human observers, reducing the time between detection and follow-up observations. This automation is essential given the transient nature of these objects and the vast amounts of data generated by modern telescopes. Furthermore, the development of a global network of observatories sharing data in real time is essential. The ability to quickly confirm a discovery and initiate follow-up observations from multiple locations around the world is critical for accurately determining an object's trajectory and gathering comprehensive data before it fades into the interstellar void. This collaborative approach, leveraging the strengths of different telescopes and geographical vantage points, will be key to maximizing our scientific return from each new interstellar visitor. International cooperation and data sharing protocols are being established to facilitate this global effort, ensuring that no interstellar object goes unobserved. The ultimate goal for interstellar object research is not just to detect them, but to study them up close. The fleeting nature of Oumuamua and 3I Atlas highlighted the challenge. By the time they were discovered, they were already on their way out of the solar system, limiting the time available for detailed observation. This has spurred discussions and preliminary designs for dedicated interstellar intercept missions. Such missions would involve rapidly launched spacecraft designed to rendezvous with a newly discovered interstellar object, ideally while it is still inbound or near its closest approach to the Sun. These probes would be equipped with a suite of instruments capable of performing detailed analyses of the object's composition, surface features, and any outgassing activity. Imagine a spacecraft flying alongside an interstellar visitor, taking high-resolution images, analyzing its chemical makeup, and even collecting samples. This would provide invaluable data that simply cannot be obtained from Earth-based observations. Concepts like Project Lyra, a proposed mission to ʻOumuamua, demonstrate the feasibility and scientific appetite for such endeavors. Even if Oumuamua itself is now too far away to intercept. While Oumuamua is out of reach, the lessons learned from its study are directly informing the design of future missions to intercept other interstellar objects. Beyond direct interception, future studies will also focus on laboratory experiments to simulate the conditions and processes that might have shaped these objects. This includes recreating the extreme cold of interstellar space to understand the stability of exotic ices, and simulating impact events to understand how objects like Oumuamua might have acquired their unusual shapes. Advances in computational modeling will also play a crucial role, allowing scientists to run complex simulations of interstellar object formation, ejection, and evolution, providing theoretical frameworks to interpret observational data. These simulations can help to constrain the possible origins and compositions of interstellar objects, guiding future observational campaigns. One of the most ambitious proposals is the development of interstellar interceptors, spacecraft designed for rapid deployment. These would not be traditional, slow-moving probes. Instead, they would leverage advanced propulsion technologies, perhaps even nuclear thermal or laser sail concepts, to achieve the incredibly high velocities needed to catch up with these fast-moving targets. The challenge is immense, requiring breakthroughs in propulsion, navigation, and autonomous operation, as the window for interception would be incredibly narrow. However, the scientific payoff, direct sampling of material from another star system, is considered by many to be worth the monumental effort. The development of such technologies would not only benefit interstellar object research, but also open up new possibilities for rapid solar system exploration. Furthermore, the study of interstellar objects is not limited to physical samples. Spectroscopic analysis from Earth-based and space-based telescopes will continue to improve, allowing for more precise determination of their chemical composition, even from vast distances. New generations of telescopes with even greater light-gathering power and advanced instrumentation will be able to detect fainter objects and provide more detailed spectral signatures, helping to unravel their true nature without the need for a direct rendezvous. The synergy between theoretical modeling, laboratory experiments, and observational astronomy will be crucial in building a comprehensive understanding of these enigmatic visitors. The study of interstellar objects extends far beyond the confines of astronomy. It touches upon some of the most profound questions humanity has ever asked. These objects are not just rocks or ice from other star systems. They are tangible links to the vast, unseen universe beyond our immediate cosmic neighborhood. Their study has several broader implications. By analyzing the composition of interstellar objects, we gain direct insights into the building blocks of planets in other star systems. Are the materials similar to those in our own solar system, or are there significant differences? This helps us understand the diversity of planetary formation processes across the galaxy. For instance, if a significant population of interstellar objects are indeed nitrogen icebergs, it would imply that the formation of Pluto-like exoplanets is a common occurrence in other stellar nurseries, and that these bodies are frequently ejected into interstellar space. This would fundamentally alter our models of planetary system evolution, suggesting that the ejection of planetary building blocks is a more common phenomenon than previously thought. It also provides clues about the chemical environments of other protoplanetary disks. If interstellar objects are indeed common, it suggests that the exchange of material between star systems might also be common. This raises fascinating questions about panspermia, the hypothesis that life could be transferred between planets or even star systems. Could a hardy microbe hitch a ride on an interstellar object, seeding life on a new world? While speculative, the existence of these objects makes such scenarios more plausible. The resilience of extremophils on Earth gives us a glimpse into the potential for life to survive the harsh conditions of interstellar travel, clinging to the icy or rocky surfaces of these cosmic wanderers. This opens up the exciting possibility that life might not be confined to its planet of origin, but could be a truly galactic phenomenon, spread by these cosmic couriers. While the alien hypothesis for Oumuamua remains highly controversial, the very discussion it sparked highlights the importance of keeping an open mind in the search for extraterrestrial intelligence. If we are to truly search for signs of advanced civilizations, we must be prepared to consider all possibilities, even those that challenge our conventional understanding. The study of interstellar objects provides a new avenue for SETI, prompting us to look for anomalies that might suggest a technological origin. The sheer improbability of Oumuamua's shape and acceleration, when viewed through a purely natural lens, continues to fuel this debate, reminding us that the universe may hold surprises far beyond our current imagination. The future of SETI might involve not just listening for radio signals, but actively searching for physical artifacts traversing the cosmos. a concept known as archaeological SETI. This shift in perspective, from passive listening to active searching for physical evidence, could redefine the future of our quest for alien life. Ultimately, the study of interstellar objects reminds us of our interconnectedness with the broader galaxy. We are not isolated in our solar system. We are part of a dynamic, interconnected cosmic ecosystem. These visitors from other stars serve as a powerful reminder of the vastness and wonder of the universe, and the endless possibilities that await discovery. They are tangible proof that the universe is a bustling, active place, with material constantly being exchanged between stellar neighborhoods. This perspective can be both humbling and inspiring, reinforcing our desire to explore and understand the cosmic tapestry in which we are embedded. It encourages us to look beyond our immediate surroundings and consider the grander cosmic narrative, where our solar system is but a tiny speck in an ocean of stars, constantly interacting with its galactic environment. The very existence of these objects underscores the dynamic nature of the cosmos, where nothing is truly static and everything is in motion, constantly influencing and shaping its surroundings. Our journey through the mysteries of Oumuamua and 3I/ATLAS has taken us from the initial shock of an uninvited interstellar guest to the profound insights gained from comparing two vastly different cosmic wanderers. We began with Oumuamua, the first confirmed interstellar object, whose bizarre characteristics, its elongated shape, its missing cometary tail, and most puzzlingly, its non-gravitational acceleration, defied conventional astronomical explanations. It was a riddle wrapped in an enigma, sparking theories ranging from exotic ice compositions to the audacious idea of an alien probe. The sheer audacity of its behavior forced scientists to confront the limits of their understanding, pushing them to consider possibilities that were once confined to the realm of science fiction. It was a cosmic anomaly that refused to be categorized, a silent challenge to our established cosmic order. Then came 3I Atlas, detected by the vigilant ATLAS system, a testament to humanity's growing planetary defense capabilities. Unlike its predecessor, 3I Atlas behaved exactly as a comet should, exhibiting a clear coma and tail as it approached the Sun. This normalcy, paradoxically, served to amplify Oumuamua's strangeness, making its anomalies even more pronounced and pushing the boundaries of our understanding of natural celestial bodies. The comparison between these two objects provided a crucial baseline, allowing us to better categorize and comprehend the diverse population of interstellar visitors. Point 3I Atlas, by its very conventionality, highlighted the profound unconventionality of Oumuamua, making the latter's mystery even deeper and more compelling. It was a cosmic mirror, reflecting back the true peculiarity of its predecessor. Despite the insights gained from 3I Atlas, the fundamental questions surrounding Oumuamua persist. Was it truly a shard of a nitrogen-rich exoplanet? Was it a fragment of a hydrogen iceberg that somehow survived its arduous journey? Or does its unique behavior still hint at something more extraordinary, something beyond our current scientific paradigms? The scientific community continues to grapple with these questions, refining models and seeking new data to unravel the ultimate truth behind this enigmatic object. The debate is far from over, and each new piece of evidence, each new theoretical model, only adds to the richness and complexity of the puzzle. The very persistence of these questions is a testament to Oumuamua's profound impact on our understanding of the cosmos. The broader questions about interstellar objects also remain. How common are they? What is their typical composition? Do they carry the seeds of life from one star system to another? Each new discovery, while answering some questions, inevitably raises many more, pushing the frontiers of our knowledge further into the cosmic unknown. The universe, it seems, is a master of unveiling new layers of complexity, and each answer we find only deepens the mystery and expands the scope of our inquiry. This continuous cycle of discovery and questioning is the very engine of scientific progress, driving us to explore the unknown with insatiable curiosity. The universe is a tapestry woven with countless mysteries, and the arrival of Oumuamua and 3-Eye Atlas has added 2 particularly vibrant threads to its design. These objects are not just scientific curiosities. They are profound reminders of the vastness and diversity of the cosmos and the endless possibilities that lie beyond our solar system. They challenge us to think bigger, to question our assumptions, and to embrace the unexpected. They are cosmic invitations to expand our minds and our understanding, urging us to look beyond the familiar and embrace the truly extraordinary. As we continue to explore the universe, armed with ever more powerful telescopes and innovative theories, we stand on the precipice of a new era of discovery. The next interstellar visitor could arrive at any moment, carrying with it new secrets and new challenges to our understanding. It is a testament to the human spirit of inquiry, our insatiable curiosity, that we continue to reach for the stars, not just to observe them, but to understand the messengers they send our way. The quest for knowledge is an endless journey, and each new discovery, each new anomaly, only serves to propel us further into the cosmic unknown. Join us as we continue to delve into the depths of the cosmos, unraveling its mysteries, one interstellar object at a time. The universe is calling, and its stories are just beginning to unfold. Be part of the journey, subscribe to Cosmo Depth, and together, let's explore the wonders that lie beyond. The cosmos awaits, and its secrets are slowly but surely revealing themselves to those who dare to look.